A residual is no line will pass through the point, blah, blah, blah. And a definition of a residual, and look at this nice picture. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. That is, the residual is the observed y minus the predicted y, and or y minus y hat. Okay? So you can get the equation of the regression line. I'm going to shut this. And we'll talk a little bit about where the equation of the regression line comes from today. But so say I plug in 160, right? I'll get on some value on that regression line. That's what I expect. Okay? But if I take that value and the actual value at 160 is something else, the difference between that point and the predicted value from the regression line, that's called the residual. So if that residual, if that point is below the line, you're subtracting a smaller number or a bigger number from a smaller number. So in that case, the residual would be negative, right? So if the residual is above the regression line are positive and the residual is below the regression line are negative. Understand that? Okay? And it turns out that those residuals are used to calculate exactly where the regression line goes. Can I move on to the next slide? Okay. So then it says residual y minus y. So in that case, that residual would be negative. Okay. Can you see that? Maybe I should turn up the lights. It says negative residual below the line, positive residual above the line. Okay. The least squares regression line, which is what you've been doing in your calculator, okay, produce different. Least different regression lines produce different residuals. The regression line we want is the one that minimizes the sum of the squared residuals, and that's what we've been doing, which is called the least squares regression line. The least squares regression line of y on x is a line that makes the sum of the squares of the residuals as small as possible. So if I take the distance from here to here, or the difference between this point and this point, and square it, and then I take the difference from there to there and square it, and those residuals squared, if I minimize that value, okay, the difference between these points and that line squared, if I minimize that quantity, that's how I calculate more or less where the least squares regression line goes. You understand kind of what
You don't have to do that.
No, you're not going to have to do it by hand. Calculator does it before. And the reason you square it is why? Why do you think we would square it?
Very positive.
Very good, Michael. Okay, because some of these things are negative, right? Some are positive. So if you square it, and I take the smallest possible square of all those distances from that line, then that's going to give me the line that is the closest to as many points as I could possibly get. Okay, and that's called the least squares regression line, and that's what your calculator has been doing for you. Okay. Any questions on that? Okay. We can use technology to find the equation of the least squares regression line. I already showed you how to do that. We can also write it in terms of the means and the standard deviations of the two variables and their correlation. I want to show you something now. I'm going to escape because I want to bring up one of those applets that is kind of cool, but I have to get to, I have to hit pause first. Again, okay? And I go to this thing called, where is it? Data sets? No. Oh, maybe this is for teachers. Home. Here we go. Statistical applets. Okay? And I go to this thing on correlation and regression. That's what I want to do. Okay? Okay. And hopefully it will show up. Activate Java platform. Allow and remember. Later. Come on, please work. You worked at home. Come on, buddy. You can do it. It's doing something.
It's almost there.
It's almost there.
John,
Okay. Okay.
application blocked by security settings.
Okay. There it is. Click for details. Later.
That's not.
The internet
That's
here
not.
is blocked.
Ignore it. Let me try again.
That's not.
Reload. What if I reload? Let's try one more time. Is it working?
It's worth a shot.
Okay. Well, okay. And so we'll go back to here and we'll talk about we can use the technology to find the equation of least squares regression line. We can also write it in terms of the means and standard deviations of the two variables. So this apparently this formula is quite important, okay? Because it comes on the AP test, and I talked to Mr. Grace, and he said it's important. So this will be given to you on the and when you take the AP test and on my test. But this is where the slope of the regression line comes from. Okay? And so we have the data on the explanatory variable x and response variable y for n individuals. From the data, calculate the means and the standard deviations of the two variables and their correlation. The least squares regression line is the line y hat equals a, which is the what? The y-intercept, b, which is the slope, x. But in this case, b, Mike, it's not just like a normal, I mean, it is the slope, but where that b comes from is by taking the standard deviation of the x values and the standard deviation of the corresponding y values, multiplying by r, which is the correlation, and then you get the slope of the regression line. Okay? So if you were doing this by hand, you'd have to plug all the y values in, and then you have to plug in all the x values and compute those statistics on all that kind of stuff. Okay? The y-intercept, you use this equation where these two values, this one here, this is the mean of the y's. Okay? So this is the mean of the y's, mean of y's, and this one is the mean of the x's. Mean of x, mean of x, mean of y's, of the x's. And you use that to calculate the y-intercept. Okay? So I think I came up with an example, a different example than the one that's in your book to do this. Well, it was in my book, but it's not in your book. Yes.
The SY and SX standard deviations of y.
Yes, this is a standard deviation of the y term.
What's the R?
R is the correlation. Okay. Standard deviation of y's, and this is the standard deviation of x. Okay. And standard deviation of x. And this is the correlation. Correlation, is that how you spell it? Yeah, that's right. Okay? And this is slope. Okay? So, can I move on? So then, whoops, previous, had to go to previous, here we go. So, there's a close connection between the correlation and the slope of the least squares regression line. The slope is, this is, just like we said, the slope is equal to the correlation times the standard deviation y, standard deviation in x. You're going to have some problems that require you to know this. For every one standard deviation in x, the y value will change by r times sy. So all you have to do to find out, because they'll ask a question, it says, if the x values, if I move over one standard deviation in x, how much are the y values changing? Okay, and so what you do is you take the standard deviation of the y values and you multiply it by r, and you'll get that answer. As far as algebraically how it's done, don't worry too much about it. But I would write this down because it's important. Because you're going to have to use that on your homework. Okay? Because if the standard deviation were the same in both cases, or if I had a correlation of 1, for every standard deviation I went this way, I would have the same standard deviation this way. Okay? But if it's not 1, then you have to multiply by r. That's kind of what that says. Okay? So we're going to do a problem. Whoops. Where's my next problem?
Can you go back for a second?
What did I do? Go back?
Yeah.
I don't know how to do that.
Mouse.
What?
Top left.
Top left. Hit the mouse.
How you go
Thank
to
you.
the-
And now go back.
No, that's fine.
Got it.
You're right.
That's fine. Okay? Can I go to the next slide? Which is, I think it's the last slide. Okay? So here's a problem. It's similar to one in your book, but I used a different problem just so you have a different look at it. And the numbers, that one with the, what was it called? The weight loss thing. Those numbers were kind of weird. So these numbers are a lot nicer. The number of miles in thousands for 11 used Hondas have a mean of 50.5 and a standard deviation of 19.3. So in this case, they don't give you all the data. Okay, what they give you is the mean and the standard deviation of the x's and the y's. And then you have to use those two equations that I just gave you to find the slope and the y-intercept. And then use that last little thing I told you to find the equation for the least squares regression line and explain what change in price we would expect for each additional 19.3 thousand miles. Okay? So the number of miles in thousands for 11 use. So which one is the explanatory variable in this case? The number of miles a car has on it or the price that the car is? Probably the number of miles. So that's like your x. Okay? And so using those formulas, I better look at my notes here. Okay, so you have to use the first formula to find, first you have to find the slope. So B equals R times the standard deviation in y over the standard deviation in x. So you just plug that in, and R, where is it? R is negative 0.874. And if they give you a bunch of data, that would be nice, but then the reason they're not giving you a bunch of data is because if you had a bunch of data, then you could just plug all that data into your calculator and find the least squares regression line. This way they want you to use the definition of where the slope came from and where the y-intercept came from. So R is negative 0.874. The standard deviation in y is what? What's the standard deviation in y? 1899, right? This is the response variable. So that goes on the top, 1899. It's the standard deviation in y. Standard deviation in x is 19.3. And then so this comes out to be approximately equal to negative 86, if you did that. So that's the slope of your regression line. Okay? Then the next thing you do is you use the equation A is equal to, A, which is the y-intercept, is equal to y bar, which means the mean, minus B times x, which means the mean of all the x's. And they give you those numbers as well. So you want to find A. So what's y bar in this case? The mean, the advertised price, $14,425. And then minus B, which we have up here, which is 86. And, oh, it's minus, right? So it's going to be plus. You understand that? Because B is negative. So it's minus, plus 86 times times the mean, which is the mean of the x's, which is 50.5. Okay? You understand what I'm doing? I'm finding A. So that number is equal to A. All right? And if I do that on my calculator, I get that A is equal to 18,768. Okay? 18,768. And that's in dollars, which kind of makes sense. Because if I were graphing this, let's see if this graphs. Right? This is going to be a negative correlation, right? Because as the mileage goes up, the price goes down. Yes? That's why. So now we can rewrite, using these numbers, I can write the equation of the least squares regression line as y hat equals A, which is 18,768 minus 86 times x, right? And that's your equation of your regression, okay? And find the equation, so we did that, okay? Find the equation for the least squares regression line and explain what the change in price we would expect for each additional 19.3 thousand miles. So 19.3 thousand miles corresponds to one, what? Look back up here. 19.3 thousand, what's 19.3? It's the one standard deviation in the x, okay? So they want to know, when you have one standard deviation in the x, how much does the y change by, okay?
So that's what you're...
Yeah, that was that original thing. And so all you do is you take r and you multiply it by s sub y, okay? And s sub y is the standard deviation in the y. So that's going to be, so r is negative 0.874. And s sub y is 1899. 1899. And I get out negative
1659.
Thank you. Negative 1659, which means, so about negative 1660. And that's dollars. Okay? And what they say, explain what that means. What that means is for every 19.3 units I go over, right? My car price goes down by, or 19.3 thousand. It's not 19.3 thousand miles. It's 19.3 thousand miles.
The price goes down.
The price goes down by $1,660. Okay, so they might use that like Kelly Blue Book. You know Kelly Blue Book, when you're trying to buy a car or something like that, they probably use something similar to that. They take a bunch of data and they see, hey, but they use an algorithm to figure that out, and most likely they use something like this. Now, is this linear model always good? What if I was saying, why would this? What's a case in which this might not be a good model for cars?
You have really expensive cars.
Yeah, a really old, like a, what do you call those things? Like a classic car, like a, like a Model T or something, or some kind of really cool, like Jaguar, like my dad had a 1970 something Jaguar XKE 12 cylinder. It was really cool. Those ones that kind of look like
My
they
grandpa
kind
had
of look like that.
two older Jaguars as well.
Really?
Pretty classy.
They're pretty cool. 12 cylinders. And I remember when we were kids, we'd drive up to Vermont and we'd go like 120 miles an hour. And my dad was crazy in this little car. They didn't have airbags back then, and we got stopped one time. And my dad was a famous PS. Anyway, so that's how you do that. And that's all your homework, just 4 problems. You got 50 minutes or so to do it, so no whining, okay? piece of cake, right? And I could stop the show if I could figure out how to do that. There's a stop the show. And that was pretty